Hello, everyone. My name is Devansh, and I'm a graphics programmer at Supergiant Games. Today, I'm very excited to talk to you guys about the custom rendering engine that we use for the development of Hades and Hades 2. So I'm going to start with a quick introduction of our games, and then move on to do a breakdown of one frame of rendering, so we get an idea of the workload. Then I'm going to discuss some of the technical challenges that we have with our approach. And finally, I'm going to take a brief look at our rendering pipeline so that we can understand how the workload fits in the engine. I also have a slide for engineering practices. It has worked really well for us because we're a very small team of developers, 5 people. So some of the things that we've learned over the years and have worked really well. And this is not going to be a very long talk, so we can get to drinks and a lot of questions and answers that whatever you might have really fast. All right. So let's begin. Hades and Hades 2. For those who don't know, Hades is a 2D action roguelike game developed by Supergiant Games. It was first released in 2020 on PC, and it was later made available on Mac, consoles, and also mobile. It visually features an isometric stylized art style where every detail is carefully handcrafted by our content creators. Hades 2 is the sequel to Hades, which is currently available in early access on PC. If you haven't checked it out, please do. But in the meantime, I have some screenshots for you. This is a game. This is our Hades 2 game in action. This is one of the first levels. So you can see the isometric top-down view that we're famous for, and some of the action and particles that are going on in the game. This is one of my favorite levels, favorite biomes, actually. It is the Rift of Telesea. It's also from Hades 2. And a little screenshot from Hades 1. It's one of the earliest ones that we had. This is actually one of the first rooms that the player sees of Hades ever. All right, so let's begin the talk and start with the frame breakdown. We're going to be using this level from the city of Ophira as our test level for all our examples. So I want to start with 2D isometric environments, as they are one of the largest pieces of workload that we have. Most of these environments are made up of hand-painted 2D assets. These assets are drawn in our signature isometric perspective. You can imagine this perspective as a axis-aligned 2D plane that is rotated by 45 degrees and squashed in half. All of these static assets that we have in the game for all the static environments are drawn this way. You can see a texture atlas that I just pasted here, which has all these isometric assets. Dynamic objects are also part of the environments, and they are drawn in the engine with the isometric transformation applied, as I just mentioned. So things like decals, these are normal textures, but then we apply our isometric transformation in engine to apply them into the world. The camera rotation has to stay fixed for any of this to work, because, well, these are 2D assets. You cannot really rotate them and see them from any other angle. So what is the idea for doing this? Well, the idea is to create an illusion of 3D world with 2D assets. So we also don't want this illusion to be only a visual. We also want it functional. So we want our dynamic objects, like the players, the enemies, all kinds of stuff, moved between the environments, and also want movement to be possible in all 3 axes. So the X and Y axes, which is the isometric ground plane for us, and we also have a virtual Z axis, which represents an up direction. So we have a 2D game that has 3 directions, and the up direction is particularly useful when you have designers wanting to throw up projectiles, or if you have flying enemies and things like that. So all of these ideas combined give a very 3D appeal to the game, and it is actually just made up of 2D assets. All right. So how do we know what's in front, what's behind in a depthless 2D isometric world? Well, we need some kind of sorting to figure out the order of rendering. To do this, we give 3 pieces of information to our assets. First of all is the ground plane bounds. So how much an asset covers on our ground plane, in area. So we have that as a first piece of information. After that, we have a tallness parameter. And the tallness parameter is just a perpendicular height from our ground plane, which tells us how tall the asset is in our game world. And then we also similarly have a z offset, which tells us how far up the asset is from our isometric ground. So this is our virtual z-axis, which is the up axis for us. So using these three pieces of information, we are able to compute an isometric 3D bounding box. Like you can see in the picture here, like Mel is covered in an isometric bounding box. So with the bounding boxes, it becomes pretty easy. Now we are in 3D again, so we can sort all our assets and environments in a back to front order. So our map artists use individual assets and assemble them to create map objects. This is basically how we create our levels from individual assets. They group these map objects into layers, and we call these layers map groups. The map groups are naturally created by the artists in a back-to-front order. So essentially, you can imagine them like a painting. You first have the backgrounds, then some far-off objects, and then some foregrounds. So for example, in the context of the game, you can have a background layer, some floor, props, then a bunch of gameplay layers where the actual gameplay happens, where the enemies are running around, there's particle effects, there's actually objects that you can collide with. And then you can have like a lot of foreground props as well. It's important to mention that there's also a lot of layers of lighting, shading, and things like that that we have between the map groups. So this actually is very important to us because it really drastically changes the feel of a map. And this also makes our assets very reusable because we can essentially use one asset in one light setting in one place and flip it around and then use it in a different setting. Ideally, these kind of lighting and shading are done in dedicated lighting map groups, and we'll see why that is the case. All right. So after our 2D environments, the next big piece of workload that we have are 2D effects and overlays. So these are also all 2D objects, but these are not actually created at the map creation time. These are often loaded during gameplay. But they do spawn from the same points that are actually placed during map creation. So for example, we lay out enemy spawn points or fishing spots all around our levels. And then from there, the game designers can use these points to hook like enemy spawns or a variety of other things gameplay feature-wise. So what are these 2D effects and overlays? Well, some of these things include things like handcrafted particle effects. We have sprite sheet animated user interfaces. There's fonts. There's also characters, but we'll talk about them later. And then there's all kinds of screen overlay effects, the post-processing stuff, like blurs, bloom, color grading, vignettes, stuff like that. All right. So far, with this amount of workload, we have maps that have like thousands of individual assets in them. And thousands is like a low number. There's actually like, there are even maps that have like 5,000 objects, 5,000 individual assets in them. Naively rendering these artist-created map groups will really mean that we're doing too many draw calls. We're constantly resource binding and changing the pipeline states. And especially on our min-spec hardware, this is a major pixel shading bottleneck. Okay, so to alleviate some of these changes and reduce, we have some trickery that we do. The first big one is that we want to reduce our draw calls and resource updates. So what we do is, since we have so many assets that are combined together to make map objects, we actually package all these assets into tightly formed atlases. We do this with our package builder, and we do this at compile time. Since our camera is fixed and it doesn't zoom in or out too much, we have the ability to not actually use, we have the liberty, I should say, to not actually use all the MIP levels. So we can actually drastically reduce the sizes of these atlases by only using the MIPs or only packing the MIPs that we will actually use. So also, all of these assets are available, all of these atlas sheets are available for both static and dynamic assets. This idea, this optimization has been around in our engine since the time we were in OpenGL, and it still performs well. Another thing that we noticed was that all our rendering was done with like a texture quad geometry. This wasted a lot of rendering and blended a lot of transparencies. To fix this, at the time of packaging the atlases, we also generate convex hull geometry for all of our assets that can support this. So this generally gets us about 30–40% improvement in our pixel bandwidth usage. Along the same lines, we also want to reduce pixel overdraw. So we wanted to do a depth pre-pass, but it's not a 3D game. We don't really have depths. So we use our sort order depths and assign depth to each map object that we have. We then go through a depth pass and only write the opaque parts of the assets because there's a lot of transparency in them, and we want to make sure that we don't accidentally cull any pixels that will be visible because of that transparency. While doing this depth pass, we also make sure that we process objects in a front-to-back order. We already have them sorted in a back-to-front order. So they get discarded early, and the actual Z-path is faster. This optimization also further improves pixel bandwidth. There are a lot of other performance improvements that we did. Things like we noticed that we had a lot of static environments, right? Or static map groups, I should say. So like there were no dynamic objects that were going between map groups. So what we did was we decided that, okay, if the memory permits on the hardware, we can actually pre-bake all of those layered static assets into one large render target or a series of render targets, and then just render those whenever we need to, instead of rendering all of those assets in a layered map group like we usually do. On a similar line, we were also rendering a lot of overlapping lights and effects. So this, again, was a big performance hit. So what we did was we noticed that we don't really need to render these lights because they don't have very fine details, so we don't have to render these lights on full resolution targets. So we started rendering them at half resolution targets and then just sampled into the half resolution intermediate target whenever we wanted to render lighting on the final target. This helped us save a lot of pixel bandwidth as well. We already talked about atlas packing, but over the years, we made sure, like as our games evolved, we made this atlas packing smarter. So we were able to figure out, okay, so what environments are, in what map we have our environments close enough, so like if we have a house and the top of a house and the bottom of a house, we should package that together. And if that happens often in a map, then there's a very high chance that's going to happen many places in the game. We also limited the shader variety within groups. This helped us actually avoid a lot of unnecessary render pass changes and resource bindings. So far, we talked about the environments, but a big piece of our game are the characters as well. So this is a place where Hades and Hades 2 really differ. Hades actually had a very interesting and unique character pipeline where the artist would create the animations in Maya, and then they would export Bink videos, which we would just directly render in game. So as you can see, this animation of Hades, he's just actually a texture quad, and the textures are constantly streaming from the GPU every frame. So how did this pipeline really work? The artist modeled and animated the characters in 3D, and then we had a plugin to export all the render animations from Maya to Bing files. Animations had to be rotated and rendered in up to 64 different angles because, well, the characters can face like all 360 degrees, and we have to figure out the angle depending on the direction they were facing. A big advantage of doing this was that artists were able to make handcrafted changes to the frames of the video files. So we were also able to like clean up assets, add post-processing effects. We were also able to add actual visual effects that are closely knit to our player or the actual character character animation. So if the player is swinging a sword that has an animation plus a visual effects, we were able to bake that visual effect in the Bing file itself. You can see the shadow was also baked into the Bing file. Since our game had a lot of characters and the characters were made at very different scales, we had to tweak the video compression quite a lot. So we had to figure out what bitrate worked best for what scale character and like how they were presented on the screen. So this was also something that our artists could control and make sure it looked right in the game. What about low resolutions, like when the game is running at a lower resolution or a really high resolution? So we had actually a different set of Bing videos shipped with the game that supported different kinds of resolutions. So we had a 720p, 1080p, and even higher. So what was the benefit of doing all this? Well, it gave the artist maximum control. The implementation in the engine was pretty straightforward, and we were able to match the stylized look of our environments. But we also had a lot of challenges with this approach. First of all, we had to load a lot of Bing videos into memory all the time. This gave our game a large memory footprint. We also increased our size on disk because as the game progressed, like in Hades 1, by the end, we had a lot of props, we had a lot of weapons. So if our character was using a different weapon, we had to render and store all those animations again with the different weapon. Also, by the end, the iteration time was a little bit bad for the content team. The reason was if they had to change a tiny detail, but it affected all the frames of animations, they had to be rendered out of Maya, and depending on what character it was, for instance, let's say if it was our main character Zagreus, who has tons of animations, that could even take all night. Streaming large characters was a problem, especially on our min-spec hardware. We faced a lot of issues actually decompressing the video frames in time and also copying them over to the GPU. Our Bing videos were actually in 30 FPS. But we also wanted our game to ship in 60 FPS or even higher. So that became a bottleneck because now all of a sudden we cannot really show our characters as smoothly as we wanted when we were playing the game at 60 FPS. But with even all of these limitations, this was a really, really good pipeline for us, and we were able to ship multiple games with it. But for Hades 2, we knew that we had to really make some changes because we wanted Hades 2 to be much, much bigger than Hades 1. So what did we do? Well, we directly render 3D animations in Engine now. Yay. Like, it sounds obvious that we should do it, but now, yeah, we are finally doing it now. We have a faster iteration pipeline now, allows for more characters in game. We have a much smaller memory footprint. The performance is a lot better on busier levels. We have better quality for large characters because now, well, it doesn't matter. And even in early access, Hades 2 has 2 times more characters than Hades. So we still had a lot of challenges while setting up this pipeline. So it wasn't as slam dunk of a solution. The first big problem was it was really, really hard to match the handcrafted look of the rest of the environments. We had to spend a lot of time tweaking our shading. We had to add outlines, shadows, anti-aliasing. The character VFX that were actually baked had to be now done outside the game, outside the animation. And then all of this had to be done at runtime now. It was actually helpful for us to not render 3D models directly whenever we need to on the final target. We actually rendered them in a large atlas like we do for our environments every frame at the start for all the 3D models that are going to be present in the frame. And then we would just sample into the atlas and render that onto the game whenever we needed to. This prevented a lot of pipeline state changes because we don't have to render the skin shader passes all of a sudden in the middle of our 2D passes. We were able to apply a lot of the screen space effects and also the anti-aliasing to the entire model sheet at once. And we were also able to use all our 2D pipeline that existed for the animations from Hades 1, because now finally even though our animations were rendered in 3D, they were finally in a 2D atlas. So by the time we were actually using them, they were pretty much like just sprites. All right, so that was like a high-level overview of our workload. So now I want to talk a little bit about how this workload fits into our engine by talking a little bit about our rendering pipeline. So here's a brief overview of our rendering pipeline. You can look at it from the bottom left, where we start at input and gameplay. This is essentially our game thread. Here, we poll our input, we do a lot of gameplay logic, AI, physics, everything happens here, camera updates, and once the update is finished, we tell the world system, which is our really big class that handles everything from drawing to also supporting a lot of other subsystems that are actually responsible for organizing all the map objects and the map groups. So the world system initiates the gathering, sorting, and culling steps for all these map objects. And then out of that, we get a lot of drawables. These drawables are essentially data classes that contain information about how we want a map object to render in the game. So for instance, this will have transformations. This will have references to the asset that need to be used. This will have any color, hue shifts, anything that the map artist added on top of the assets. These drawables then go to our render command step. The render commands are responsible for converting the drawables into what we call renderables. These renderables have a render state and are organized into shader passes. These renderables are then forwarded to our actual API, graphics API layers, which is slightly different for all platforms. And here, we actually have several render passes and resource binding. So when we use those drawables, we organize them and actually record our render passes, fill up our command buffers, and then submit them to the GPU. So this pipeline can largely be divided into 3 steps. The first step is like the gathering and culling step. The second one is the build step, which is the render commands. And the third step is our record and submit step, which is like our last graphics API layer, which submits all the workload to the GPU. It's also important to note that all of these steps run in parallel between different frames. So we can have, if the game thread is running fast enough, we can have culling and blending being done on one thread, but as soon as it's done, the next frame can start and do it so that we're able to keep up with the game thread. So let's talk about all of these things in a little more detail. I'll start with the game thread because that is where everything actually begins. Our game thread runs parallel to the draw thread, as we discussed. It is actually 1 or 2 frames ahead at rendering. We don't allow it to go more than that because then we'll experience some severe input latency. But if the game thread is still waiting after it has like completed more frames than the draw thread, we know that there is something wrong with the drawing and it needs profiling. But there are some rare cases when there's enough delta between the render thread and the game thread, so our game thread is allowed to do multiple updates and call it one single big update and then give the results to the render thread so that the rendering can catch up with the game thread. Since our workload is generally skewed in the favor of render thread to the game thread, we offload all our Bing processing systems to the game thread as well. So, like we discussed earlier, we read Bings ahead of time and keep them cached in memory. We run the decompression jobs on the CPU. We also have the ability to run it in async compute, but based on our testing, our GPU is generally more busy than our CPU, so it always works better when we decompress our Bings on the CPU. And then we directly feed the decompressed Bing data to the render commands and skip the world and the gathering and culling stage. All right, so the next piece of the pipeline is the gathering and culling steps. Why do we need this? Well, it's pretty simple. There's just too many objects to process every frame. We'll bottleneck both CPU render thread and GPU as well. And this is especially true for our min-spec hardware. So how does this step work? The first thing we do is we place all our active objects that we have in a map in a spatially partitioned isometric grid. We cull the grid cells and then by the camera frustum, so every cell that is outside the camera frustum gets immediately culled, which culls a lot of the map automatically. Everything that's inside the grid cell now have two choices. So if it's completely inside the camera frustum, then we take all the objects. But if it's actually intersecting, then we have to check every object and the camera and see if it's actually inside or outside. Now that we have a limited set of map objects, we can create isometric bounding volumes around it with the tallness parameter, as we discussed. These bounding volumes we actually sort into a directed acyclical graph, and then we can traverse this graph to generate the depth values for each object. Then these depth values, which are just made up by us for each object, are stored in the drawable and then used for the depth prepass we discussed earlier. We also spawn several job threads and do all of this process in parallel as much as possible. After this, the drawables are emitted out of the pipeline and they go to the next step. So this is kind of like our intermediate layer between our engine and our graphics API. So what we do is we organize our drawables into shader passes. We read all the drawable data, figure out what shaders they need, what render state they need, and then we create renderable objects out of that. We are able to actually consolidate a lot of the drawables together to form renderables. Another big thing that the renderables have is that they have the resource attachments references actually built into them. These resource attachments might not be completely loaded by the time we are in this step, but if they are not, they send a signal to our resource loader and tell it to start the asynchronous allocation or update that we need at the time of rendering. The 2D renderables actually get our convex polygon meshes here from the drawables, and then they actually combine multiple of these convex meshes based on how many drawables are in a renderable to generate large triangle strips. These triangle strips are very helpful because now we can do one draw call and render like maybe 10 or 50 objects and assets. This is also the place where we do our 3D model sheet generation in case of Hades 2. Finally, this is our graphics API layer. This is slightly different for all platforms, but we can talk about it from the perspective of PC. So this part, as I mentioned, is the graphics API code, and it records and submits command buffers to the GPU. That's the final goal. We iterate over the renderable meshes and draw them into our render passes. And we start these render passes and then add our resources, the buffer and texture resource views, to the descriptors. We organize these descriptors. We have organized these descriptors into per frame, per pass, and per draw sets to minimize the number of updates we have to do. We also add our wait semaphores for any of the resource loader operations that we have asked for. They happen on a different queue, or if it is available, for example, the copy queue. For some APIs, we also have to add layout barriers to change the resource states. And then, so for example, any render target that we have written to, and now we want to use it as a render target again, then we have to apply these layout barriers. And finally, we record and submit all of this to our command buffers and submit it to the GPU. For submission, we use a triple buffer swap chain to present, and finally, we have our output on the screen. So, finally, before I conclude the talk, I wanted to talk about some of the engineering practices that we have in our company. It is a very small team of engineers, only 6 engineers right now. And we have we've had these practices, we have developed them over the couple of years, and they have worked really well for us. So I want to mention some of these that are really close to me. Yeah, so the first one is from me. Start out simple and then iterate. This has gotten me so many times since I started my career because when there's a new feature to develop, there's so much excitement, there's so much research, and then we develop something really elaborate which has a lot of bells and whistles. But then when we give it out to the content creators to actually use it, there are several things that they don't use, or it's just not useful for the context that they need the functionality for. So it's generally better that we start out simple and then iterate so that we can create a small prototype, hand it over to the content team, and then see how they run with it, if there's something that we need to add, or if the idea is completely bad. Setting limits and embracing them. Well, in Hades, we had a lot of map groups, like we discussed, and we didn't have that many limits on how many groups we can have, how many objects we can have inside them, how many different kinds of objects that we can have inside them. So generally, it had worked well for us until now, but in Hades, the artist made really elaborate maps, and it was really, really exciting to see them. They were really beautiful. But at one point, when we were rendering on our min-spec hardwares, we noticed that the performance wasn't up to the mark. So in Hades 2, we decided that we're going to start early at setting the limits, and we're going to embrace them, and so that everyone from the team and the content creators to designers, everyone know them and are able to make a game that will run flawlessly on all platforms that we want to support. Profile early and profile often. Well, this is kind of similar to setting limits early, essentially. We want to profile early because we want to know how much headroom do we have for our limits. We want to profile often because we are constantly adding new features, we're constantly adding more content, the levels are getting busier and busier. For those who know and play Hades on higher heat levels, things can go really crazy. So we really want to profile the game constantly, especially in these busier levels, so that there are no surprises, essentially. Go the extra mile in terms of quality assurance. Well, this is something that we did for Hades 2, where we actually launched the game as a technical test on Steam and had thousands and thousands of players actually enroll to this test and play the game. The game was essentially bug-free to us in our QA, but when thousands of people played it, we were able to get a lot more bugs from that testing. This testing enabled us to have a really, really clean release in our early access. And we were really happy about it, and it made the release process so much smoother. Keeping the tech stack small and maintainable, well, that's kind of explanatory itself because, well, we're a very small team. We are very, very careful about adding new features, and we are very careful about how we will maintain them. And finally, having a product-first mindset. At the end of the day, the users see the game, and that's what they care about. So we really, really want to have a product-first mindset. So that was my talk. Thank you so much for listening. If there is any questions.
Yeah, we definitely have some time for questions, so I'll run around a bit.
Hi, so you talked about for the maps that there was significant amounts of 2D lighting applied to change the look. Could you go into a little more detail about how that's authored and also how it's applied in the engine?
Yeah, it's really just not very different from the assets themselves. The artists draw the lighting assets. We do the isometric transformation on those lighting assets, and then we essentially blend them. The artists create assets in a way that they can compose them in layers. So the lighting doesn't exactly look the same because it's using the same asset. There will be several layers of lighting on top of each other. So it would really, really look organic and fit the level.
Thanks.
Hey, let me know if I misunderstand, but if you do the CPU decompression, that'll increase your bandwidth usage. And the main question I have is actually if you explored using the Vulkan video extensions that came out a couple of years ago.
I actually, sorry to interrupt, I cannot hear you very
Oh, you can't hear me?
Yeah,
I'll try
yeah.
again.
It's better.
If you're doing the decompression on the CPU, that's going to significantly increase the bandwidth usage. And I was wondering if you go a bit more detail into that. And the other part was if you explored using the Vulkan video extensions that came out a couple of years ago.
We have not explored the Vulkan video extension, but that's really a good idea. I think I'll take a look. Right now, our Bing workload for Hades 2 is much less than the previous game because, well, we don't do characters with them. So it's really only used for, I think, what it was intended for, full screen videos. So this is not a problem for us anymore. But, I mean, if it ever is, I'll definitely check it out. Thank you.
Hi. First, I wanted to say that I played Hades 1, and I had no idea that the main character was a video, so kudos. Can you comment on the Bing performance, even if just for the full screen video that you now use?
Yeah, Bing is very, very good. The compression is really fast, and like, you know, if you have a reasonable amount of data to copy, you can actually make it work really, really easily. The bigger problems, I think, with the Bing were not at runtime, but I think they were at the content creation side for us.
Okay, any particular number for decompression time?
Not off the top of my head, especially since it was the previous game.
Thank you very much.
Did I miss one?
Hi. I think, if I understood correctly, you mentioned that you baked shadows into the animation in the video clips for Hades 1. So how do you deal with that in the context of like overlap or layering? Because shadows kind of work on a different plane than like the actual character, right?
You're right. It doesn't really work. So if you notice, you can check out the game and like, so for instance, there's like flashing effects. So when the character gets hit, it flashes white. Well, its shadows also flash white because it's like the same sprite sheet. So yeah, it just doesn't work. We try to avoid it actively when creating the content.
Okay, so one in the front.
So very unique visual style, even more unique rendering pipeline. I was just curious if at any point, because you guys kind of make similar, have a similar visual style to Arc System Works for Dragon Ball Fighters, Baz Blue. You both kind of target the 2D aesthetic using 3D. So I was curious if you had any commonalities, were inspired by any of their work, anything of that sort.
Yeah, so I did definitely took a lot of the looks, like when we were going to do all our like animations in 3D, and I always took a look at all the stylized games that were out there, like Borderlands, like any of these things. I took a look at the shader. But I think, in particular, I don't think like any of the work was like completely in our context. So these were like, the changes in the shader were really tweaks suggested by our artists to make, which were applied to all our characters, and also they were essentially parameters that the artist could tweak so that they can get the shading right. So there wasn't like a uniform technique that we could get from those games, but definitely, yeah, there was a lot of inspiration, and just them existing gave us confidence that, yeah, we can also do it.
Thank you.
Okay, I know that we said last question, but I'll run for some more. I need to make my steps today.
Was there any particular reason why you went with atlases instead of bindless? Like, was there any hardware requirement that prevented you from going full bindless, at least for textures?
Yes, so this optimization was done at like OpenGL time. So we're like, this might even be before Hades one, but it still works really well for us. But yeah, bindless is on the radar for sure. Like, I think moving forward, bindless could be a good way to do it as well.
Hi. I see that a lot of artwork is involved in your games, and I'm wondering, do you use some AI tools for optimizing the job of the artist, or everything is drawn by hand?
No. I don't think we use any AI. It's all very carefully hand-drawn. Takes a lot of time and effort.
Okay. Thank you very much for your talk.